First off, I'd like to thank the organizers for inviting me to speak. I'm going to be talking about K-tilings of the Aztec diamond, which are going to be, instead of a single tiling of the Aztec diamond, we're going to have K different tilings, and there's going to be some interaction between them. And this is based on joint work with Sylvie, who is here, and her student, Andrew Gitlin, as well as some work with Matthew Nicoletti. Okay, so the plan for the talk is to first do a review of just normal tilings of the Aztec diamond. Probably some of this material was already covered in Sylvie's lectures, but it'll be useful for us to see it again because we're going to do basically the same thing once we introduce the K-tilings. So after we do that review, we're going to discuss, or we're going to introduce the K-tilings, and we'll relate them to interlacing partitions, tuples of interlacing partitions, LLT polynomials, and some integrable colored vertex models. So then we'll prove some results, or state some results and prove some results about these K-tilings. And if there's time at the end, I'll describe a shuffling algorithm, a generalization of the normal domino shuffling for these tuples of tilings. Okay, so let's review tilings of the Aztec diamond. So these were introduced in 92 by Elkes, Cooperberg, Larson, and Propp. So we'll have some diamond region of a checkerboard, and we're going to tile it by dominoes, where each domino covers two adjacent squares. So here is one tiling of the rank 3 Aztec diamond. By the rank, I just mean the number of faces of our checkerboard along each edge. So here's rank 3. But you can ask, what does, say, a uniformly random tiling look like for a very large rank? And so here I think is rank 256 or something like this, 200. And it's well known that the domino tilings exhibit the limit shape phenomenon. So generically, they'll look like we'll have some frozen regions in the corners where all the dominoes are in a fixed orientation, some disordered region in the center where the dominoes are kind of wild, and some boundary between these frozen regions and the disordered region. And it's known that as you take the rank to infinity, this boundary becomes a deterministic curve. And in this case, it's just a circle. As you can see already here, it looks pretty much like a circle. So we'll see similar but more complicated limit shape behavior for the K-tiling. So now let's talk about a little bit of the combinatorics of our domino tilings. We're going to assign particles and holes to our dominoes, or to the faces of our checkerboards, according to the rules up here, so there's 2 types of vertical dominoes and 2 types of horizontal dominoes, depending on the checkerboard coloring. And one type we assign holes to, and the other type, or one type we assign particles to, and the other type we assign holes. So in my pictures, I'll mostly just omit the holes and only draw the particles. So here are 2 examples, one where all the dominoes are horizontal and one more complicated example. And now what we're going to do is we're going to look at the diagonal slices of our Aztec diamond, and we're going to think of these particles living on the diagonal slice, and we're going to map them to the Maya diagrams of. So just a reminder of what I mean by the Maya diagram of a partition. So say we have the partition 4, 3, 2, 2, 1. We're going to draw it where we have a row of 4 boxes on the bottom, then a row of 3 boxes, then a row of 2 boxes, 2 boxes, and 1 box. And now whenever we see a vertical step on the outline of our diagram, we're going to draw a particle. And whenever we see a horizontal step, we're going to draw a hole. And we're going to think of there being infinitely many particles going up along the y-axis and infinitely many holes going to the right along the x-axis. And now if we just look at this sequence of particles and holes, this is our Maya diagram. So there's just a sort of a bijection between partitions and these sequences of holes and particles. And I wanted to note that there's a unique center of these diagrams, even though they're infinitely long in both directions. There's a unique center where the number of holes to the right of the center is equal to the number of particles, or the number of particles to the right of the center is equal to the number of holes to the left. So here are 2 examples, 4, 3, 2, 2, 1, and then the empty partition, where in this case, all the particles are just fully packed to the left. So if we look at the tiling with only horizontal dominoes, and here I have this red line to indicate where we're going to view the center of these Maya diagrams. Then we see all the particles are fully packed kind of to the bottom left. And so this gives us a sequence of partitions, empty, 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 all empty partitions. And a thing I want to note is that it's not true that we can have any sequence of partitions and have that map to a tiling. There's some restrictions on what partitions are allowed, and we call these interlacing conditions for the partitions. So probably Sylvie talked a little bit about this in her lectures, but for the domino tiling, what needs to be true is that the sequence of partitions we get has to follow the pattern that you start with the empty partition, you add a vertical strip to get your first non-empty partition, then you remove a horizontal strip, then you add another vertical strip, then you remove another horizontal strip. So I'm not going to go into a ton of detail about this, just to say that there's some interlacing conditions that are required to get a bijection between these sequences of partitions and the tilings.
Could I just ask, please, is the center of gravity constant in this diagonal sequence?
Yeah, the center for all our Maya diagrams will be, always think of them as being centered at 0, where there's the number of particles to the right and the number of holes to the left is 0.
You think?
Or equal. The difference is 0. Yeah.
But I mean, I guess it's kind of trivial, but just to make sure. So in the Aztec diamond, when you have these particles, then you define that on the bottom left, there are particles at infinity. Right?
That's right. Yeah, you should think of this as
it's always in that orientation.
Yeah. So down at the bottom left, you should think of infinitely many particles going off, and to the top right, infinitely many holes. And so these interlacing conditions force that the only interesting things that can happen will happen in this Aztec diamond region.
You said that there's a unique spot where you could draw the red line.
Mm-hmm.
If there were to be many holes, could you move the red line through these?
So usually, what do I mean to say? So this notion of like there being a line where you could look at the number of particles to the left and number of holes to the, or number of particles to the right, holes to the left, and count the difference. This is normally called the charge of the Maya diagram. So in more general contexts, people let the charge also vary, and you allow the center to vary. But for us, for our bijection, it's just constant. We look at charge 0. So here's another example of a tiling of rank 3. And here, if we look at the second slice, so the second diagonal, we see that compared to being fully packed, each of these two particles has each jumped 1 place. So that's the partition 1, 1. Just a way to read off these partitions from our tiling. So now we want to add weights to our tiling. So we're going to add weights to the vertical dominoes. So there's 2 types of vertical dominoes. And so we're going to have 2 parameters for the different types. So whenever we have a vertical domino with the black square on the bottom, and it's on slice 2 minus 1, I guess, whose top square is on slice 2i minus 1, we're going to give it a weight of xi. And similarly, we'll give a weight of yi for dominoes where the black square is on top. All the dominoes get 1, weight 1. And our goal for the first part of this talk, it'll be to compute the partition function of these tiles. So here is an example. So we can see on, say, slice 3, there's 1 vertical domino, which has the black square on the bottom, and the white square is on slice, I guess, 2 times 2 minus 1. So that gets an x2. And since that's the only vertical domino of that form, the weight of this tiling has a single x2. And just as an aside, you can write these weights in terms of Schur polynomials. So in fact, the weight of a tiling is a product of Schur polynomials where the indexing partitions are related to the partitions along our slices. So it's an example of a Schur process, and there's been like a lot of theory built up around how to analyze these Schur processes. But that's about all I'll say about the Schur process. So now we have this formulation. We had this formulation in terms of Maya diagrams, and now we're going to give a separate formulation in terms of vertex models. So we're going to look at path configurations that look like this. Well, here the different colors, rows, are going to indicate that we're using different weights. So we're going to have 2 sets of weights, and one set we're going to draw always in purple, and the other set we're going to draw in gray. And the way we'll identify this with the tiling is we'll look at the horizontal slices between rows, and we'll look at where the paths cross these horizontal slices. And we're going to identify that again with a Maya diagram of a partition. And so we'll have a sequence of partitions, and it'll be the same sequence of partitions we saw in our tiling. So yeah, and the nice thing here will be that these vertex models we're using are Yang-Baxter integrable. So they satisfy the Yang-Baxter equation. So we'll be able to kind of swap the rows using the Yang-Baxter equation to make things easier to compute. So the convenient way, or the reason we reformulated in terms of this vertex model is so we can use the Yang-Baxter. So here I'm just drawing our two vertex models. Here are the local weights at a given. I'm using vertex and face interchangeably. So I'm drawing faces here, but I've been saying vertex. So there are 5 vertex models. The pads only have 5 allowed local configurations. This is some degeneration of just the normal 6 vertex model. And so we have one purple 5 vertex model, and then a different gray 5 vertex model. And yeah, here are the weights and how they work. It's not so important what they are. It's important. The important thing is that the weights match up with our domino weights, and it's Yang-Baxter integrable. So now, like I said, we'll have a bijection between tilings and path configurations on this lattice by looking at the sequence of partitions. So we take our tiling, we draw the particles, we read off our sequence of partitions, then we assign these particles to the horizontal slices of this lattice, and then that uniquely determines the path configuration. And so that gives us our bijection, and it's a fact that the weights are the same up to some overall factor, but the overall factor doesn't depend on the configuration, it only depends on the rank, and we'll just ignore that in the end. So like I said, this is a Yang-Baxter integrable vertex model, so we can look at these cross weights, which I've drawn in yellow, and we have the Yang-Baxter equation, which allows us to swap gray and purple squares. So here are the weights you get for the crosses. And now what can you do? This is kind of a standard argument for these vertex models. You can insert a cross on the left of a row. You can push it all the way across, and that will amount to swapping the 2 rows. And because of the specific boundary conditions we have, we can then peel off the cross weight on the right, and it just adds an overall factor. So we're allowed to swap rows up to some overall factor of 1 over 1 plus x1. And this is nice because it makes the partition function very easy to compute. So we can start with a vertex model where we have all the gray rows on the bottom and all the purple rows on the top. And then we'll just repeatedly use the Yang-Baxter equation to swap rows and keep track of all the factors we get every time we do this. And eventually we can swap all the rows until we get the lattice model we want, where the purple and gray alternate. And we know that the partition function of this will be the partition function of the thing we started with gray on bottom and purple on top, times some overall factors. And it turns out this thing with all the gray rows on bottom and all the purple rows on top has a single allowed configuration. All the paths are forced to just go up and right. And so the weight of that you just write down, and that turns out to be the overall factor we're just going to toss out. And as a result, we get that the partition function for our Aztec diamond has this nice product formula, which is well known. This is just,
So this is equivalent to the McDonald, what he called little omega involution.
I actually do not know what that is. I'm not sure.
It's just what takes you in the ring of symmetric functions. It takes the elementaries into the completes and vice versa.
Yeah, Sylvie nods her head yes to me that it is.
Yeah, I think so. I think we agreed the other day with that.
Okay, one other thing to note is that this row swapping is also equivalent to like a Cauchy identity for the Schur polynomials. So how you would normally do this in terms of Schur processes would be like repeated applications of the Cauchy identity. And kind of in the vertex model world, that's repeated applications of Yang-Baxter equation to swap rows. Yeah.
Is this the original proof of this number of tilings or not?
Not really. I think it maybe, I've never seen it formulated exactly like this before, but it's kind of no different than like proving it via the Cauchy identity, right? I'm just writing the Cauchy identity in terms of a vertex model.
Super nice.
Yeah. So it's formulated slightly different, but so just to recap this bit, we have a bijection between tilings and interlacing partitions, which we use to get a bijection with the vertex model. And then in the vertex model language, we can compute the partition function easily. So now we're going to try to redo this exact story, except with a more complicated model, this time the K-tiling. So let's talk about the K-tilings of the Aztec. So now what are we going to have? Instead of a single tiling, we're going to have, say, 3 tilings, or in general, K. We're going to draw them in different colors, and we're going to think of them as being ordered. So in this case, like blue is a smaller color than red, which is a smaller color than green. And for each tiling, we have a sequence of partitions. So now we're going to have a sequence of tuples of partitions that interlace in this Aztec diamond way. And later, when we have a vertex model, instead of a single 5-vertex model, we're going to have K superimposed copies of the 5-vertex model, which will have some interaction weight. So what are the weights? We're going to have the normal, xi's and yi's that just bias the vertical dominoes, just like before. But now we have our interactions, where for every pair of colors A less than B, we're going to get a power of T if when we superimpose the tilings, we locally see something that looks like this. So we just draw our tilings on top of each other. We count every time one of these configurations occurs, and we give that a power. Here, blue is smaller than red. So let's look at an example. So we have these X and Y weights coming from just, vertical dominoes in each of our tilings. But now if we look at this, say, highlighted blue domino and this highlighted red domino, if we superimpose these tilings, those 2 dominoes will look like this. So this counts as an interaction between blue and red. So that'll count one of these powers of T. And if we look at red and green, now red's the smaller color and green is the larger color. And this highlighted red domino and this highlighted green domino look like this, which is going to be an interaction between red and green. So it turns out in this example, there are, I guess, 11 total interactions, and those are 2 of them. So in the end, we're going to formulate this as a vertex model, and we need to be able to compute the partition function. We need the Yang-Baxter equation to hold, and having different powers or different T's for the different colors breaks the integrability. Yeah. So really, I'm kind of telling the story in reverse. We started with a vertex model and then knew how, this method for constructing tilings, and we just looked and checked what our tilings looked like. So our interaction is really coming from we had a Yang-Baxter integral vertex model, and this is what it said. Okay, so before we get to results, I want to just show a bunch of simulations. So these are all done with a domino shuffling algorithm that I'll hopefully explain at the end if there's time. So here is rank 64, 2 colors, and T is equal to 1. So when T is equal to 1, they're just independent tilings. And keeping T is equal to 1 and making the rank 256, we start to see, the normal Arctic circle that you expect for domino tilings for both colors, since in this case, they're just independent. But now suppose we turn T on and say T is equal to 5. So this is still rank 256. We see much more interesting limit shape behavior. Now it's kind of this oblong shape, and there's a cusp forming in the bottom region. I don't know if it's very clear in the picture. But, and if we zoom in, so I zoomed in on the southern corner, you could really see this cusp here. And if instead of a 2 tiling, we look at a 3 tiling, now it's kind of hard to tell, but it appears that there's going to be 2 cusps. And so just to say that the limit shapes seem very interesting and complex. And so now here's T less than 1. So this is T 0.2. And in this case, it's kind of oblong, but in the long in the horizontal direction. And now the cusp is on this top left boundary. And as we take T to 0, this cusp starts to dominate, it becomes very large. It actually pushes out the frozen region of vertical dominoes that was in this corner. And it has this straight line boundary with the frozen region of horizontal dominoes. So the cusp just becomes so big, it actually lose the cusp in our limit shape or in our Arctic curve, and it becomes something convex again. Okay.
Is there any connection between this T and the T in all polynomials? All Littlewood polynomials?
Yeah. So this T is kind of the T in LLT polynomials, and for LLT polynomials with a certain choice of tuple of partition, certain LLT polynomials are actually just equal to the whole Littlewood polynomials. So it is sort of is related, yeah, through the relation with LLT.
So the partition function is the LLT.
So in this case, you'll be able to write like for the normal Aztec diamond, you can write the partition function as a product of Schur polynomials, or you can write the weight of a tiling as a product of Schur polynomials. And in this case, you'll be able to write the weight of a tiling as a product of LLT polynomials. So it turns out the partition function will have just a nice product form, but for an individual tiling, the weight is a product of LLT polynomials.
I'm not exactly sure what it means, but does that mean it's a special case of a McDonald process?
I'm not 100% sure. Well, yeah, I'm not 100% sure. There is some relationship between the LLT polynomials and the McDonald polynomials, but how that translates exactly into the tiling, yeah, I can't really say. Okay, so yeah, this is just what I said. So for these K-tilings, the weight of a tiling is now going to be, or is given by a product of certain things called co-inversion LLT polynomials. And originally we were studying a vertex model for these polynomials, and that's where our vertex model came from, that we use then to construct the tilings. Okay, so now we're going to formulate this in terms of a vertex model and then use Yang-Baxter equation to compute the partition function. So the way it works is almost exactly how it worked for the normal Aztec diamond. So I'm not going to give like every single detail. But now we're going to have K copies of our previous vertex models. We're going to superimpose them, but draw them in different colors. And they're going to have some interaction weight that corresponds to the interaction between our dominoes. And we want the Yang-Baxter equation to still hold. But just to mention that our vertex weights are actually like the analog of a 5-vertex limit. It won't have 5 vertices anymore, but it's the analogous limit for some an R matrix that was written down by Agrawal, Borden, and Wheeler related to UQ SL1K, so supersymmetric SL1K. And so our Yang-Baxter equation, we just inherit from taking limits of their Yang-Baxter equation. Okay, so for example, the purple weights we're going to use. So now they're exact. So let's look at a particular color, say color A. We can look at, there's still only 5 local allowed path configurations for this color. And the weights are the same as before, except now whenever you see an X, you're also going to get a T. So it'll be X times T to some power, where this power depends on the colors greater than A. And it's going to be the number of colors greater than A that take the form just a vertical line. And so here's an example of like a configuration at a row. And you can look in the first square, we have a blue path going to the right and a red path vertical. So the blue path going to the right gets an X, but also there's a color larger than it that's vertical. So you also get a T. This is an example of what the weights look like for the purple. And there's a similar story. So the total weight of a vertex is just the product of the weights of all the colors. And then there's a similar story for the weights of the gray. They're a little more complicated, so I'm not going to write them down, but it more or less works exactly the same. So you can define the weight of the color to have the factor of T included, and this factor of T, the power of the factor of T depends on the other colors in the face.
Okay.
Yeah. And so, for example, in this first face, we have an XT from the blue and then a 1 from the red. So the weight of this face is X. Okay, and these weights or these vertexes satisfy the Yang-Baxter equation. And in this case, it's the same kind of deal. For the color A in our cross, the weights look exactly the same, except every time you see a Y here, and now it's also a Y times the power of T, and the power depends on the other colors present in that thing. All right, and then using the exact same proof as before, where we put all the gray rows on the bottom and all the purple rows on the top, use the Yang-Baxter equation to swap them a bunch, you can prove that the partition function for our Aztec diamond has this nice product form. I don't want to go into the details. It works exactly the same. Yeah, it's nice. It still looks very pretty. So let's look at some special cases. When T is equal to 1, it reduces to just the normal Aztec diamond partition function to the kth power, as you'd expect, because when T is equal to 1, they're independent. But kind of surprisingly, when T is equal to 0, the only terms that survive are when the power of T was 0, and you get exactly tiling or the partition function for the Aztec diamond back. So somehow, when there's the same number of tilings when T is equal to 0 as there are normal tilings of the Aztec diamond of the same rank. And we could actually give a nice bijective proof of this. So that's the next thing I want to do. I want to prove this fact that when I send T to 0, I get back normal domino tilings. And it's easiest to do this in terms of Schroeder paths. So the Schroeder paths are just a way to a bijection between your domino tilings in certain non-intersecting paths. And you get them by just assigning paths to your dominoes according to these rules. So here on the bottom, we have all the rank 2 domino tilings and the corresponding Schroeder paths. So if we interpret our interactions in terms of these paths, what we get is that whenever a blue path hits a red path from above, that's an interaction, or when they both go up together, that's also an interaction. So we're going to think of only 2 colors for the time being, just because it's simpler. So here's an example. If we look at the highlighted dominoes, we look at the Schroeder paths, we see that we'll have a blue path coming down and a red path going horizontally, and they intersect with the blue path on top. So that counts as an interaction in our Schroeder path. So that gives us a power of t. So now we want to take t as to 0, and this is going to impose really strict restrictions on how the Schroeder paths are allowed to behave. So for example, if we just look at this top path, the one that starts here and ends at the other dot labeled 1, now what can the paths do? If they both went up at the start, well, this would count as an interaction. We get a power of t, so that's not allowed. So what if the blue went up and the red went to the right? Then since they end at the same spot, eventually the blue has to come down and meet the red. And since the blue will be on the top, that'll give us an interaction. And so that's also not allowed. So in fact, the blue path, the first step of it is forced, and it just has to go horizontally. And you can do this same sort of analysis for all the paths, and you get that there's a large region of paths that's completely forced to just be horizontal. So then the way this bijection to a normal tiling of the to a single tiling of the Aztec diamond works is that you look at all your forced paths and you delete them from your configuration, and then what's left, you just slide down and right until it matches up with the boundary conditions, and it turns out to be a valid tiling of the normal Aztec diamond. So we have a nice geometric proof of the fact that the partition function when t is equal to 0 is just the normal partition function for the standard Aztec diamond. Okay. I like this proof. I think it's very cute. So this actually is useful for computing the Arctic curve when t is equal to 0, because it's nice and geometric. And we know what the Arctic curve is for the normal Aztec diamond. It's just a circle. And if we kind of follow this bijection in reverse, we can get the Arctic curve for t is equal to 0 back. And it's not a circle anymore. It's piecewise ellipses. So still, not super complicated, but more complicated. And here it is overlaid on the simulation. So one thing to note is that both colors have exactly the same Arctic curve, which is kind of surprising because our interaction was not symmetric with respect to the colors. So this is something we don't really understand. We somehow get some asymptotic symmetry that isn't really apparent in the discrete version of the model.
Like you said, t equals 0, you are back to the usual situation.
Yeah, there's a bijection to the usual situation. And so when t is equal to 1, they're independent and both of them are just the normal thing. But when t is equal to 0, there's a bijection from our K-tilings to a normal tiling. And if you just follow that bijection, you can compute what the Arctic curve for the K-tilings will look like. And this is what it looks like. Okay. So other things we know there's a reflection symmetry between t small and t large. In particular, t to infinity is the same thing as kind of t is equal to 0 when you flip over the line y is equal to x. So this we can prove. But otherwise, we can't really say much for generic values of t outside of these special values. So it would be really nice to understand, what tools are required to understand, say, the Arctic curve for a generic t or the fluctuations. Sort of the normal tools don't seem to work.
You use the word costs. Do you think there will be a singularity or?
So I'm trying to think if there are. So if you look at, say, lozenge tilings of trapezoids, you'll also see these kind of cusps in there. And I think these will behave like the same. I think probably, I don't know for sure, but I think probably it'll be the same as those. All right. So in the last few minutes, I want to describe a shuffling algorithm. So this is a way to generate random K-tilings. So K-tilings where the probability you get a specific tiling is proportional to the weight of the tiling. So this is how I did those simulations. And it's pretty much a, straightforward, well, it's maybe a little surprising that it works, but it turns out the algorithm is, almost exactly the same as the original domino shuffling algorithm, a prop for people familiar with that. And that original domino shuffling algorithm could be used to do a lot. It was very powerful. And for example, they used it to compute the Arctic curve of the domino tilings. So the hope is maybe in our shuffling algorithm, we could use it to prove some stuff, but we haven't really been successful yet. And this is based on work with Matthew Nicoletti. So let me just walk through how the algorithm goes. So we start with the rank 0 tiling, and then there are 4 possible rank 1 tilings. I've just drawn them here. We're always going to work in 2 colors here, but it generalizes to K colors. So I've drawn the 4 possible rank 1 tilings and their weights, and we're just going to pick one with the appropriate probabilities. So one way to do this is to have the blue tiles be vertical with probability t over 1 plus t, and choose them to be horizontal with probability 1 over 1 plus t. And then after we've chosen the blue, pick the red to be vertical with probability 1/2. So that's step 1. We generate a rank 1 tiling. And now every step of this algorithm is going to grow the tiling 1 higher rank. So let's suppose we've run it a bunch and we have some rank K tiling. The next step is to embed this in a 1 larger checkerboard, and now slide the dominoes according to some rules. So whenever you see a vertical domino with this parity of squares, you're going to slide to the right, and so on. And if ever 2 dominoes collide, they slide into each other, then you're just going to delete those dominoes from the picture. So if we look at that example, and we look at these 2 center dominoes, well, the top one wants to slide down and the bottom one wants to slide up. So they collide and we just delete them. And so they're just gone from our picture, and this is what everything else looks like after the sliding. And now I've swapped the checkerboard coloring so it matches our original convention with the black on the top left boundary. Okay, so now we have a partial tiling of rank K plus 1, and we can uniquely partition the empty space into 2 by 2 squares with the black that have a black square on the top left. Yeah. So we uniquely cut our untiled space into 2 by 2 squares, and now we just fill that in. So how does that work? We first are going to fill in every blue square, and we're going to choose to fill it with 2 vertical dominoes with some probability t to number 1 over 1 plus t to number 1, where this power of t is determined by what the red configuration looks like. So if in that square red looks like this, or red needs to be created, then you get a power of t, and otherwise you just get 0. So you fill in all the blue, and now all the blue is filled in, and now you look at red, and here blue, because we filled in blue first, so now we can just fill in red. And again, the probability that you pick vertical dominoes is the power of t depends on what the blue looks like locally. I say I filled it in like this. Here are the probability that each of these choices come. And you just repeat this and grow your tiling over and over again until it becomes rank n, whatever rank you want, and then you're done. And it's a theorem that the probability that you get a specific 2 tiling of rank n is just its weight over the partition function of the model. So in this case, I set all the x's and y's to 1, but you could also include them and it still work. So I don't think I really have time to discuss the proof because I'm basically done, or basically out of time. But the idea, one way to prove it is to generalize the spider move or the urban renewal move that you can use to prove the normal domino shuffling for people familiar with domino shuffling. But it's more complicated and it ends up not working as nicely. So the normal domino shuffling, you can actually include completely general weights for your tiling. And here we can't. It doesn't seem like we're able to include more weights than just the weights I described in this talk. Okay. So you can prove it a similar way, but it doesn't work quite as well. Yeah.
Generalizes to K-tilings.
So it's fairly straightforward. The only difference is you know, these probabilities now don't just depend on red, it would depend on every color larger. And then here it would depend on like both the larger colors and the smaller.
I mean, you can show for each K that you get the correct probability in the end.
Yep. And okay, so the summary, we can construct these K-tilings and they're related to, you know, LLT polynomials and these colored integrable vertex models. And in certain limits, we can actually prove some things about the Arctic curves and other symmetries of the model. But for generic K, we don't know much at all. And also we have this nice domino shuffling algorithm for generating tilings that generalizes the one-up problem.
Okay, thanks a lot for the nice talk. Any question?
So you mentioned that the way the work was done was in the reverse order from how you presented. So
Yeah.
does it mean you actually started with the R matrix or with the model, vertex model?
What we did was we started with wanting to come up with a vertex model whose partition function was the LLT polynomials. And so this was work with Sylvie and a few other people. So we came up with this vertex model, which is related to the gray weights I had here, not exactly, but pretty close. And so we came up with this vertex model. We wrote a paper about that. And then later, Borden and Agrawal and Wheeler, they like almost simultaneously, they wrote a paper where they were studying the R matrix you get from UQSL1K. And they showed that it was exactly the same, or like a degeneration of that was the same thing as the vertex model we had come up with. So we didn't really start with the R matrix. We kind of just started by messing around with LLT polynomials.
One possibly actually start with an R matrix, look at the corresponding model, and then after that, try to study the potentially related combinatorics.
So you're saying like, if I just, you know, you give me some R matrix, I look at some analogous 5 vertex limits, then I put those together and try to come up with some domino tiling for these sorts of weights.
Or some combinatorics.
Yeah, and yeah, in principle, yes. I think the nice thing about R's is when we use the Yang-Baxter equation to swap the rows, we always just picked up an overall power, right? Like in general, it might not be true that you could pick boundary conditions where that's the case, right? You could try to swap the rows and that will give you like a sum of different boundary conditions on the end. Like so, but in principle, you could try.
So is this like a whole research program?
So not exactly how you would describe that, how you described it, but it is, there's a ton of papers on like vertex models that relate to specific symmetric polynomials. And this is like a huge like factory of work, like, you know, any symmetric polynomial you can think of, someone's probably written a paper on how it's related to some vertex model. So in that sense, yes.
Any other question from the audience before John?
Yes, this is just a comment. You know, the Maya diagrams were originally introduced by Sato in relation to integrable systems and infinite Grassmannians and so on. But he did something more general than that, which maybe is the apparatus that is the equivalent or the fermionic equivalent of, I mean, when I say fermionic, the interpretation of the Maya diagrams fermionically. They're basically a basis for a fermionic Fock space. And that is the so-called multi-component KP, which takes the same Hilbert space and basis and exterior basis, but it labels the bases in a different way, mod K. So instead of doing the integers, you have a pair of integers. One is, you know, how many times, what the division by K gives you, and the other is the residue. So it's just another way to label the integer lattice with 2 integers instead of 1. And that gives you, I mean, in the applications to integrable systems, it gives you a very good fermionic way to express the so-called multi-component integrable hierarchies. It seems to me that this mod K labeling of the Maya diagrams might possibly be of use in your K tilings, but maybe not.
It does sound very like similar, at least. Yeah, that could be a good thing to look at.
So, you have a question. Okay, so let's thank the speaker again.